So we're going to start studying exponentials, okay? Functions that curve when you graph them up very sharply, or it can also go down very sharply. Okay? We'll talk about growth and also decay. So let's look at the difference between those two. In the first one, x squared, what's my base? X. My exponent? 2. In the second one, that's switched. In each case, we still have a base and an exponent. But once you put a variable as an exponent, it's no longer a polynomial. X squared is a polynomial. Specifically, it's a quadratic graph. 2 to the x is not. Okay, that's called an exponential. So anything that has a variable as the exponent is an exponential. Okay. Also, if you were to compare these two functions, I know a parabola curves up pretty quickly, but 2 to the x is going to curve up even quicker. Because imagine plugging in like 5, or we'll go even bigger, plug in 10 for x. If you plug in 10 in the first one, what's 10 squared? 100. Now, if you plug in 10 in the second one, that's 2 to the 10th, which is a lot bigger than 100. So 2 to the x is going to curve up very quickly. Let's take a look at what it looks like. It starts out kind of flat. And then all of a sudden, after the number 1, is when it really starts to curve up. The bigger the base on an exponential, the faster it curves up. Okay, so when you have a variable in the base and the exponent is a non-negative integer, that's a polynomial. That's what we did back in chapter 3. Variable in the base, like x, and an exponent that's non-negative integer, like cubed. So like y equals 5x cubed minus 8x plus 7. That's a polynomial. Okay. So now when the exponent, when the variable is in the exponent, that's when we have an exponential. Now, I'm saying here that the base has to be a positive real number that's not 1. Why not? Why wouldn't something like that be an exponential? I mean, 2 to the x is
1.
Yep.
1 to any power would still be 1.
Yeah, this is basically just like saying y equals 1. Okay, that's not an exponential. Also, I say that the base has to be a positive real number. Okay, we're not going to be dealing with a negative number. Okay, because all kinds of weird things happen if you have a negative base on an exponential. Like, think about this.
It'd be really cool though.
Right. So if you tried to graph that, and you let x equal 0, you'd get 1. If you let x equal 1, you get negative 2. If x is 2, you get 4. If it's 3, you get negative 8. So it seems like it's kind of oscillating. But then we could get into saying, well, what if we let x be a decimal? Like, if you let y equal, let's say you tried to do this. What does the 1/2 power mean?
Square root.
Means to do with square root. You can't take the square root of a negative. That's imaginary. But if you did 1/3, you could do it, because 1/3 is a cube root, and you can take the cube root of a negative. So then we start getting into really weird things. Some positive values, some negative values, some imaginary values. And in fact, the calculator can't graph that. If you type it in, you'll get nothing. All right? So we got to stick with bases that are positive. Okay? Exponent can be anything you want. All right? But the base has to be a positive number. Not equal, it can be a decimal, that's fine, like 0.2. You could do that. 0.3 or 1/2 as a base, sure. Okay. But no negative numbers in the base. So let's look at this exponential function again. What does it look like the domain is?
Infinite.
Yeah, it goes forever to the left, and it will go forever to the right. It's going up quicker than it's going to the right, but it still is going to go to the right. Now, how about the range?
Infinite. 0 to infinity.
Does it reach 0?
It doesn't work here, so.
No, it's actually an asymptote. Watch what happens if you start plugging in negative numbers.
Like,
you can
like the thing I'm trying to achieve is like 0, and then like.
You can see with negative numbers you're getting decimals. Right? -5, -7, -9. It's getting close to 0, but it never will be 0. How come? Why can't it ever be 0?
It's pretty much just square rooting that positive number over. Like, if you have a negative, like, exponent, it's just like, it's like putting it into, like, fraction form.
Yeah, so like if you had this, what does that mean? 2 to the -10th.
That's like 1 over 2 times, how many times? Like, so, 2 times, I don't know how much it is, but, well, 2 to the 10th.
2 to the 10th. So basically when you have a negative exponent, it's just 1 divided by a huge number. I don't care how big of a number you do. You can do 1 over 2 to the 500th power. It's still not going to be 0. Right? The only way it could be 0 is if the top is 0. And the top can't be 0, because the top is the number 1. Right? So it's an asymptote. So the domain, -infinity to infinity. And again, this is saying what I just wrote on the previous page. The base can be any positive real number except the number 1. So we already wrote that down. Thanks. Those are all examples of exponential functions. They all have a number in the base. They all have a variable as the exponent. I didn't say the number couldn't be irrational. It can be, like pi. That's fine. Square root of 2 as a base? Sure. Just as long as the base follows this condition. It's some positive real number, not 1. These are all examples of things that are not exponentials. What are the first 2?
Quadratic and quartic, or no, cubic and quartic.
So we have a cubic and a quartic, which are 2 types of polynomials. These are both polynomials. You could think of this one as 1/2 x to the 4th. That's the same thing. This one is kind of a hybrid between a rational function and a radical. Okay? If you didn't have this, I would say it's what we did in chapter 4. Either way, it's still not exponential. But now it's what we call rational. When you put this in here, I'm not even sure what you'd call it. It's not exponential. That's all I care about. Right. So any questions on why these are exponentials and why these are not? Okay. So I kind of already gave this away, but let's look at the difference between 2 to the x and 3 to the x. Okay. What did I say happens with 3 to the x?
You just slopes up faster.
Yeah, it's going to curve up faster.
I was listening class, Chris.
So we got 2 to the x, watch 3 to the x. You'll see it curve inside the blue line to the left of it, because it curves up faster. Now, if you zoom in, you're going to see that they actually switch places, which one is on top. So we're kind of focusing on what happens around 1. They're going to cross at the point 1, 1. I mean 0, 0, 1. So at first, the red one is underneath, and then at 0, 1, it goes on top. It's kind of like the behavior we have with square roots, where the behavior changes at a certain point. It changes at 0, 1. All right. So if we want to analyze an exponential graph, one thing we're going to have to make sure we do is that it's written kind of in this format. If you had something written like this, that's not really what we want. We'd like to have it written as a base without a negative exponent. It just makes it easier to think about. All right? So let me show you how we can fix if something has a negative exponent, just to kind of write it a little differently. Remember, when you have a negative exponent, it means to put it in the bottom of a fraction. Okay? So now, let's think about this one. A to the negative x. What number is in front of the x?
1.
It's like a negative 1. So you could, I'll just kind of put a step in between. You could think of it like this. A to the negative 1x. Now, when would you end up with a number times a number in an exponent? Think about what's the rule for when you multiply exponents
You
together?
raise a power to a power.
A power to a power. So you could think of it like that. A to the negative 1 to the x. That's a power to a power. You multiply them to get negative x. And now, I just told you what a to the negative 1 is. So substitute that right there. So, what ends up happening is if you raise something to a negative x, all you have to do is take your base, flip it, and you can make the x positive. Okay? Whenever you're comparing functions, you always want the variable positive. Okay, any questions on that? So just take your base, flip it, and then the x becomes positive because of what I just showed you. Okay, so let's look at these. The reason that I think these are kind of hard to compare with the negative in front of the x is because when I look at this, I know that this is a decay graph. Most people that are just starting wouldn't know it's a decay because with decay, you're supposed to look for a fraction, like a base that's 1/3 or 1/2. When people look quickly at that, they say, oh, both have a base of 2. They must both be growth. But it's not because this negative is messing it up. So how can I rewrite g of x?
1/2 x.
It's 1/2 to the x.
3 to 1 press.
Okay. Now I can tell g of x is what we call a decay function because the base is less than 1.
Forgot the caret. I'm sorry. Forgot you were happy.
Hey.
Caret.
So I want to look at finding the domain and range of each of those. 2 to the x we've already done. Does anyone remember, I'll just kind of quickly sketch it. It looked like this. What was the domain for 2 to the x? Negative infinity.
Positive infinity.
To infinity. And what was the range for 2 to the x?
All the numbers except 0, or all positive real numbers except 0 to positive.
Yeah, so 0 to infinity.
Can you take
Without-
the lead boy?
1, right?
No, it does go through 1.
Oh.
Yeah,
40 minutes. I have to come back.
like if this is your axis, it'll hit 1 at some point.
Throwing every question. Just go in.
Now let's graph 1/2 to the x. Okay, again, after a while, you're just going to kind of know what this looks like. But 1/2 to the x.
We can have the curve. The regular one. So it's going to be shallower. It's going to be like, it's going to be like the leaning tower of Pisa. It's not going to be like a straight up line. It's going to be like a crooked line.
Chris, have you always had there?
No, right.
That's not it.
I'm not sure this is a good fit.
Oh, no, we had to do with them all actually in geometry class.
So
I don't know.
that's the 1/2 to the x. What's the domain on that?
Negative infinity.
It's the same domain. It's a mirror image. If you were to graph 2 to the x, I could have kept it on there at the same time. But they are mirror images over the y-axis. So negative infinity to infinity. Infinity to infinity. And what's the range?
All real
Infinity.
numbers. Or all
Infinity is
positive
0.
numbers.
Yeah, all positive real numbers. Or 0 to infinity. Yep. So actually, exponential growth and decay functions can have the same domain and range. It's just one curves up as you go to the right, one curves down as you go to the right. Okay, but same domain and range. So, now I just kind of want to generalize that. Instead of doing specifically 2 to the x and 1/2 to the x, I mean, we could do 3 to the x, and 4 to the x, and 5 to the x. I just kind of want to look at a general pattern. So, a is a positive real number. 2, 3, 4, 5, anything. Let's start with f of x. That was the growth function. So, as x, look at the one in red. As x went to the right, what happened to the y value? The one in red approached infinity. Yep. Now, as x, we're still looking at the first one, okay? Looking at the y value again. But what happens as you head to the left to the graph in red? It approaches 0. Okay. Now we're going to look at the same thing for g of x, which is when you have a fraction as a base. Okay, so I'm just kind of generalizing the idea of when you have growth and when you have decay. So 1 over 2, 1 over 3, 1 over 4, some positive real number. Okay. So look at the graph in blue. What happens to the graph in blue as you head to the right?
It approaches 0.
Right. If you have a fraction, like the one in blue is 0.5, 1 over 2, approaches 0. What if you head to the left?
Approaches infinity.
It approaches infinity. Okay, and that's always true. When you have a base greater than 1, you have growth. When you have a base that's between 0 and 1, you have decay. If you have exactly a base of 1, neither. We just said 1 to the x isn't an exponential at all. It's just a straight line. It just said. So the difference is basically whether the base is greater than 1 or between 0 and 1. So greater than 1, we get growth. Between 0 and 1, we get what's called decay. Okay. Any questions on that? All right. So let's look at this. I'm going to put the other page back up, but I want to take those two graphs that I just had and plug in a negative for x. So I want to basically replace x with negative x and watch what happens. So take f of x and replace it with negative x. What would f of negative x equal? Yeah. Well, before we jump too far ahead, like if you just plug in that for the variable, what would you have first? You'd have a to the negative x, which we just said a to the negative x is 1 over a to the x, but look what happened. That's the other function. So when you replace in f of x, if you change x to a negative, you get the other function. How about if you replace this with negative x? What would you start out with?
A to the x.
No. In function g, if you just replace the variable with that, what would you start out with?
Negative
1 over a to the negative x.
1 over a to the negative x. Well, if I write that here, 1 over a to the negative x, when you have a negative, that means to do what to your base? Flip it. So that's really a to the x, which is the other function. So what that basically proves is that those are mirror images of each other. That's how you can prove graphs are mirror images. If you replace your variable with a negative and you get the other one, in both cases, then they are mirror images. So I kind of said they were mirror images, but that proves it. So if I had like 2 lines, y equals 2x plus 3, and y equals negative 1/2 x minus 4. If I wanted to know if I graph these, are they mirror images of each other? replace x with a negative right here, and see if you get the other one. In this case, you don't. These are perpendicular, but they're not reflections of each other. To be reflections, I could do something like y equals 2x and y equals negative 2x. Those would be reflections. All right. So, we can transform exponentials exactly the way we've transformed every other function all year. Okay? So, let's see if we can list the transformations needed to change f of x into g of x. First, anyone think they can tell me how many transformations are happening?
2.
More than 2.
Four. From f of x to g of x or in total?
From f of x into g of x. Like take f of x, do this, 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 and this, and you get g of x. How many thises are there?
3.
There's only 3. Okay. So to get g of x from f of x, what would be your first step?
Y times 2.
No, you can't say add, subtract, multiply, or divide.
Shift
Okay.
5 up.
No,
No, shit.
That's a vertical. That's vertical.
down, but I'm not sure if that's for.
What's the, well, that's always the last thing, right? Vertical shift out of all 6 steps, you have 2 shifts, 2 stretches, 2 reflections. So there's 6 different things that can happen. Vertical shift is number 6. That's the last one you would
So
always
a
do.
vertical stretch by 2.
Vertical stretch is not the, that's,
What's that add 1? Please tell me. I don't know what
First,
adding, what sort of transformation that is.
side.
It's not a reflection because it's not negative.
what's that? What's the first transformation you always deal with?
Horizontal.
Always do horizontal shifts first. Second thing? Then you do horizontal stretch. Third thing, if you had it? Vertical stretch is the 4th thing.
There's a reflection.
Reflection.
Horizontal reflection. It's always horizontal, horizontal, horizontal. Now we deal with the stretch. These 2 you can switch, it doesn't really matter. As long as you do the shift first, and then stretch or reflect, either way. And then stretch or reflect for the verticals, either way. So vertical reflection. I always do stretch, reflect, stretch, reflect. I do it in that order. And then the 6th thing, vertical shift. Remember, shifting is when you add or subtract. Stretching is when you multiply. Or divide, I guess. Reflections are when you have a negative. Horizontal stuff is always inside the function. Vertical stuff is always outside. Also, horizontal stuff is always backwards. It's the opposite of what you would think. Vertical is not. If you see a +3, it's a up 3. If you see a -2, it's a down 2. Okay. So that kind of summarizes everything about transformations. Okay, so let's look at this again. So what's the first thing that we have in g of x? We have a horizontal shift because we are adding inside. When I say inside, this is inside. That's your function. The 2 and the -5 are outside. All right, so what's the +1 going to do? Shift left 1. Do we have a horizontal stretch? No, if you did, it would be like a number in front of the x, like 2x + 1. Okay, stretching is always multiplying the variable, and it's inside. Do we have a horizontal reflection? No. That would be a horizontal reflection. We don't have it. Do we have a vertical stretch? How much?
Factor of 2.
Vertical stretch by factor of 2.
Like, wouldn't that change the y from like a 9 to like a 27?
Do we have a vertical reflection?
So it's a 2.
No. Now you do. Okay, you'd have to have a negative in front of that too. Do we have a vertical shift? Yes. Which way? So shift down 5. You don't have to say vertical shift down 5. Like when you say down, down is vertical. I get that. Same thing here. You don't have to say horizontal shift left 1. I know left is horizontal. Okay, left or right, up or down. So you always have to give the kind of transformation, shift, the direction, and how much. Stretch, how much. It's a shift, the direction, how much. And that's how you do number 2. Okay. Any questions on that? Let's look at this. So when you quickly look at those, you may think that they are different, but apparently they're the same because the directions are asking you to prove that they're the same. Now, to prove they're the same, you start with one of them and you change it into the other. So let's try to change f of x into g of x. Just looking at it, just my thought. So f of x equals that. What could I do first to just make it look a little bit more like g of x?
Rearrange the power.
Yeah, fix the power. Make it, put the variable first, because that's how it is in g of x. So you can at least do that. Plus 3. Now, we still have to do something else with the power. Does anyone see what you can do here? Or factor out, yeah, factor out something. What would you want to factor out? Factor out a negative 2. If you factor out a negative 2, what are you left with here?
X minus 1 minus
X. So we're getting there. Okay, if you factor out a negative 2, you're left with that. Now, what can you do? 2 to the negative 2 means what?
1/4.
It means one. It means this. 1 over 2 squared. Okay. I'm just simplifying that part because what I basically have here is I'm multiplying two things together. Okay. The only way I could multiply these together, maybe it's better to think of it this way. What's the rule for when you multiply two exponents? Power to a power. So this must really be this. Power to a power. I think that's probably clearer to say it that way. It's a power to a power. And now, 2 to the negative 2, you guys just told me is 1/4. What's 1/4 as a decimal? 0.25. And now we've proved that f of x is the same as g of x. So the reason you might have to do that is if you have to compare functions. Like, you might look at that and say, oh, well, one's growth, one's decay. No, they're exactly the same thing. There's no difference between the two. The other way this might come up is if you ever have to write your own exponential, maybe it's a multiple choice question. And you get the answer f of x, and I write it like g of x. Okay? Because I always like to put the variable first in the exponent. You just have to see that your answer and my answer are the same. Okay. Any questions on how we prove that? And it's not a very long proof, maybe 4 steps. 4 steps or so. All right, let's look at this for a second. We're going to talk more about this tomorrow, but I just want to show you this graph. It's kind of a interesting graph, especially if you try to think about what happens as x approaches infinity. So, what's happening to the part that I circled as x approaches infinity?
it approaches 1.
Approaches 0.
Yeah.
It's 1 because it's 1 plus.
The part that I circled approaches 0, right? If x is a million, you have 1 divided by a million. Okay. Now, let's kind of expand that out a little bit. What does that approach? That approaches 1. So you're taking a number that approaches 1 and you're raising it to a huge power. Well, if you take 1 to a power, what do you get? You always get 1. So you're taking a number that's getting closer and closer and closer and closer to 1 and raising it to a larger and larger and larger power. So let's see what happens. You can't do 0 because that'd be a divide by 0. So it's in 2 pieces. And there is a vertical asymptote here. It's just very steep. Let's look at the table. So if you plug in like 10, you get 2.59. So that would be 1 plus 1/10 raised to the 10th. If you plug in 25, you get 2.66. Okay. If you plug in 100, you get 2.70. It's not going up very quickly. I mean, going from 10 to 100, I went from 2.6 to 2.7. I went up 1/10. Let's go to 500. Now I went up from 2.70 to 2.71. Right? So what does it look like is happening? As x gets bigger and bigger, is the y value getting bigger and bigger? No, it's approaching something. Right? So look at the difference between 1,000 and 5,000. 2.7169, 2.718. That's a difference of 2 thousandths by changing your x value by 4,000. So it's getting closer and closer to this number 2.718. Okay, it's actually 2.718281828. It doesn't keep repeating 1828. I don't remember the next number, but it's not a 1. And this is a special number known as e. Okay, we're not talking about logarithms today, but we are talking about exponentials, and this is kind of like an exponential because you have a variable as an exponent. The base is also a variable, which makes it different than an exponential. A real exponential has to have a fixed number as the base. This doesn't. Okay, but it does have a variable as an exponent. So whether you go to the right or you go to the left, the y value is approaching 2.71828. And that is this number, second divided by, that's the number e. So kind of interesting is you have a number that's getting closer and closer to 1, and you're raising it to an infinitely large number, and it just happens to approach 2.7. Just kind of proving that beyond what we would do in this class. But it is a number that's going to come up a lot tomorrow when we do logs.
It's just like, I feel like life just has like random numbers where it's just like, you know what, this is going to be a thing. Like a mole. Like where did that
Okay, so last thing we're going to look at are the formulas for exponential growth and decay. So let's say that you had a population of a town, we call the population P, and it's increasing at a rate of R. Okay, R could be 2%, 3%, 5%. It's some percentage. So at year 0, when you first measure the population, it hasn't increased at all yet. It's the beginning. So what's the population when we begin? P. Now, if the population went up, say, 2%, what would you multiply a number by to increase it by 2%?
1.02.
You could multiply by 1.02, or you could take the original population you had, and what would be 2% of that?
R.
Wow.
P
P times 0.0.
P of R.
P to point, what is it? Point
0.02.
0, 2. So if you take a population and you add 2% to it, that's what this is. You guys said 1.02p, that's the same thing. I want to think about it like this though. So it's
Like I said,
p
it was hard.
plus 0.02p, or population plus population times the growth rate. Now, what do those both have in common? A what?
They both have P.
They both have p, so I factored it out. So that's the formula for the population after 1 year. Now, when we started year, let's look at this. When we started year 0, the population was p. Okay? Now, after year 1, that's my new population. So when I start year 2, what's the population starting at year 2 now?
The one you just ended year 1 at.
The one we just ended year 1 at. So in general, it's always population plus the increase. So now my population is p times 1 plus r. And now, how would you figure out an increase of that? What would you do to say find like 2% of that?
You would do the same thing that you did in the first place. So you would just put that inside the parentheses instead, and then put p on the outside.
So if you wanted to find out 2% of that, what would you do? Multiply by 0.02. If you wanted 3%, 0.03. If you want r percent, basically just put an r in front of it. So I already have that written right here. There's your initial population, plus, you could put an r after it in front of it, it doesn't matter. Take your original population times your growth rate.
Wouldn't you need that first p inside the parentheses there? Like, because right now, aren't you distributing like both the p and the r into the same bracket?
Yep, that's a double that's distributing p and r. Like if you do something like this, you're distributing the 3 and the 5.
So it could.
You can put them both together in the front if you want, and do it like that. And with numbers, you can actually simplify it and just say 15.
So it can be PR.
Yeah, you could put PR. Now, the reason I wrote it like this, though, is because I want you to see what they have in common. What do both of those red boxes have in, like, what is, on row 2, what do they both have in common?
P times R.
I'm going to factor that out. So I have a P times 1 plus R. And if you factor that out, well, if you factor P times 1 plus R out of that, there's nothing left there. So you got to keep something. So you're left with just a 1. What if you factor a P times 1 plus R out of the second one? You're just left with this. So if you factor out the P1 plus R, you're left with just an R. So you have P, 1 plus R, 1 plus R. Just rearrange, I factored it. What's 1 plus R times 1 plus R? It's 1 plus R squared.
I don't know.
So at the end of year 1, you had P times 1 plus R to the 1. At the end of year 2, you had P times 1 plus R to the 2. At the end of year 3, it would be P times 1 plus R to the 3. At the end of year T, it's P times 1 plus R to the T. And that is the exponential growth formula. Where P could be an original population, it's an original amount.
See a teenager with that hair. I don't like it one bit.
Okay, R is your rate of increase, but it has to be as a decimal. And T is time. Usually time is in years most of the time.
T is time.
T is time. Yep. Now, for exponential decay, you only have to change one thing in that formula. make it 1 minus r. Everything is the same. P is an initial amount. R is a rate of decrease, okay, as a decimal. And T again would be time. Okay, so let's try an example. It says that a town has a population of 50,000 people going up at 2.5% every year. Basically write a function for that, and then we're going to use our calculator to figure out when the population hits 100,000 people. So we're going to write population as a function of time. What's my initial amount?
50,000.
So 50,000 times 1 plus r. What's my rate here? 2.5%. What about as a decimal?
0.005.
So r is 0.025 plus 1.
1.025.
1.025. One more thing I need. To the power of t. That's my function. Now they want to know when the population hits 100,000. So how, where would the 100,000 get plugged in?
P to the power of t.
P of t. Replace that with 100,000. Now we're not going to solve it algebraically because we have a variable in the exponent. The only way we can solve variables in the exponent is with a logarithm. So we'll do this exact problem later when we do logarithms. But how would I do it graphically?
100,000 is one value, and then 50,000 times 1.025.
Yep. So 50,000 times 1.025 to the x. Just fix your parenthesis. Took a while. What should I set my y max to?
125,000.
Yeah, at least it's got to be above 100, or I won't be able to see it.
5 should do.
Does negative values for x make sense?
Nope.
No. X is or t is time. I don't know how many years it's going to take. I'm going to guess that this happens within 30 years. Maybe it happens a lot sooner. Let's hit graph and see what we got. So there's my line at 100,000. And there's my population. It's going up very slowly, so it almost looks linear, but I think I've got enough of it. You'll see it as a curve. Just barely.
That's a long time.
So it's just a little under 30 years. Second calc, intersect,
Think about that on like a global scale. Like,
28.07.
population yearly double in like 30 years. What do you think the planet's going to do?
Okay, so the time, it's about 28.07 years if the population goes up at 2.5% every year. So basically, I just asked you, how long is it going to take the population to double? That's another way I could have worded this question. All right, so let's take a look. So as always, be careful when you're graphing it, whether or not you include negatives. Most of the time, if you're dealing with like people, negatives don't make sense. Time doesn't make sense to be negative either. Okay. Let's look at a specific type of growth, which is doubling. Okay. We're going to start with 100 bacteria, and it's going to double each hour. So 0 times 0 means the beginning. How much bacteria was there in the beginning? 100. How about after 1 hour? 200. And then? 400. But I want you to think of it like this. It's the original amount times 2. The original amount times 2 to the second power. The original amount times 2 to the third power. The 2 comes from the fact that you're doubling. Okay? And the exponent is coming from how many times you doubled. At hour 3, you've doubled, doubled, and doubled. Well, if you double, 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 that's a factor of 8. Okay? On the 4th hour, you would have doubled 4 times. And doubling 4 times means it's now 16 times as much. After t hours, you would have doubled t times. So, this is the formula for a bacteria doubling. Now, in the problem I just did, how quickly did it double?
Every hour.
Every hour. So I didn't even really need this part. But this, right here, that I just circled, that whole thing, that's the number of doubling periods that have happened. So number of doubling periods. Because let's say something doubled every 7 days. And I said 14 days have gone by. It hasn't doubled 14 times. Unless it's doubling every day. But I said, no, it doubles every 7 days. So if something doubles every 7 days, after 14 days, how many times has it doubled? Twice. It's gone through 2 doubling periods. 14 divided by 7 would give you 2. So you have to make sure that this exponent is the number of doubling periods. If it doubles every 1 unit, then you don't need the denominator. Okay? But it's the initial amount times 2 to the t divided by the length of time to double. So, suppose we have 100 bacteria, doubles every hour. I want to know when there will be 350,000. Okay. So, let's start with the equation. So let's write bacteria as a function of time. What would I write first? 100. Yep. Times 2 to the t, and what's my denominator? 1. Okay, it doubles every 1 hour. Okay. If it said it doubles every 3 hours, I would put a 3 in the denominator. That way, if 12 hours had gone by, 12 divided by 3 means it would have doubled 4 times. Okay, but it's doubling every hour. Okay. And then, how would I finish off the question?
Plug in 350,000 for bacteria.
Yeah. Is there any question on how I'd finish that? Just like the last one. Okay. And I can give you an estimate very quickly of when it happens. So if it doubles every hour, that's 1 hour, 2 hours, 3 hours, 4 hours, 5, 6, 7, 8, 9, 10, 11.
Well, around 12.
Between 11 and 12 hours. Because I had to double 11 and 12 times. Okay, so it's between 11 and 12. You just have to get the decimal.
So you would graph that and you could find the exact number?
Yep, just like we did the 28.07.
Right. Okay.
Yep, same thing. Okay, so last thing we're going to look at is what's called half-life. It's the opposite of doubling. Okay. Half-life measures the amount of time it takes for half of a substance to decay. Right? So usually this is used with like radioactive material because it's harmful, and they'll measure how long it takes for that substance to become non-harmful. Some half-lives are thousands of years. So meaning like if you created, say, 100 pounds of nuclear waste today, and it had a half-life of 1,000 years, that means 1,000 years from now, half of that material will no longer be harmful. Okay, it will have decayed. And then after another 1,000 years, half of that will no longer be harmful. Okay? So it's basically, it's never really zero, but eventually after enough time, could be millions of years, it'll be negligible. Okay? It won't be harmful. Yeah, medications have the same kind of thing, like a certain half-life. So if you take like an Advil at time 0, it's like 100%, and then after a certain amount of time, maybe that there's only half the medication left in your system. Okay? Maybe it's I don't know what it is, but the medication decays in your system. So the formula for decay is initial amount times, and it's half-life. So we do 1/2 to the t divided by the length of the half-life. If the half-life is every 1 unit, you don't need the denominator. If it's not, then you need it. So let's set up an equation for that. The half-life of a radioactive substance is 20 days, and you're starting out with 5 grams. So what would be my equation? So the amount is what? 5. And what's the length of the half-life? 20. So what's my exponent? T divided by 20. So after 20 days, how many half-life cycles have gone by? 1. How about after 80 days? We've had 4 half-life cycles. So now, when will there be less than 1 gram remaining? How would I do that? So put in what?
One of those, just 1.
So yeah, just put in 1.
And then 5 times a half t over 20.
5 times a half raised to the x over 20. Okay. How many grams are we starting with? 5. So I don't need to go to 125,000. So we're starting with 5. It's never going to reach 0. We're going to have half, half, half. It's never going to decay to 0. That's an asymptote. So there's our line at 1. There's our substance decaying. So it does not hit less than 1 in the first 30 days. Let's go like 75 days.
Yeah, how would that work?
75 days is almost how many half-lives? Almost 4. So this looks like it happens maybe around 60 days, which would be about 3 half-lives. Let's see. I just guessed 60. That's 46. So a little over 2 half-lives, about 46.4 days. And make sure you answer it correctly, because it says, when will there be less than 1 gram? After 46.4 days. Not at 46, after. Okay, so that's the homework for
I mean, I guess
tonight.
but you also have to consider.
Tomorrow, we're just going to look at half of a section, 5-4 part 2.
It's not really saying.
And we'll be finishing up 5-4 part 2 on
There's something that big happening to affect the world.